I didn't realize I wasn't recording yet. I thought like okay. Thank you like for reminding. I always forget it. I say sorry about that. Like it's getting seen now. So so okay, like let me maybe repeat a little bit. So the problems we are trying to, because I just start recording, is trying to solve is like this one. That is a problem we left out last time, and we will use this like um right away actually, hopefully like in this class. And then like we can absorb the constraint as I said last time, like using Lagrange multiplier, and this is the Lagrange multiplier here. Maybe use a different color. So this is the Lagrange multiplier. So we absorb the constraint there, then this become an unconstrained optimization problem, and then I can just um, take the gradient and set it to 0, then I will get this. And we what we know now is that x is the eigenvectors of A transpose A. Now and then like let's say we just like write x. Actually, when we know this is an eigenvector of x, maybe like I don't even need to decompose that. So now, actually, I can even skip that because I already have this information that x is the eigenvectors of x. Now, think of like I have like the eigenvectors, let's say maybe v1 up to vn, right? And I have like lambda 1 up to lambda n, and we will just like let's say like lambda 1 up to lambda n, they are like kind of like sorted ascendingly. Then now x should be one of the eigenvectors, right? Which eigenvectors I should pick? First of all, I will assume all these eigenvectors are normalized already. And if it's normalized, then x will be any one of these, right? Because any one of these, this constraint will be satisfied. If they are normalized, this vi will all equal to 1. Now, which one I should pick? It should be one of the eigenvectors, but which one? So we can just try it, right? So let's say if I compute like A transpose A, V here, right? Vi, let's say I just pick any Vi here. This is from the eigenvector. And we see like what's the value of this. A trans Vi transpose A Vi, that's equal to um AVI is like lambda I VI, right? And this is like AVI transpose. Actually, this part is like AVI transpose, and this actually is lambda I VI as well. So then I will have like just lambda transpose. That's just lambda itself, lambda I here, and VI transpose lambda I VI. This is just scalar. I can move them together. So lambda I transpose is just itself. So lambda I square Vi transpose Vi. What is this again? So this should be just 1, right? This is just the norm of like Vi. So if we assume like all of this is normalized, it will be just equal to 1. So therefore, this is just lambda I square. So as you can see, like for any of the eigenvectors, if I compute like Vi transpose A Vi, what I get will be just the eigenvalues, the square of the eigenvalues. So now if I want to minimize this term here, x transpose AX here, so we can simply pick the eigenvectors of the smallest eigenvalue, right? So therefore, like the solution is simply V1 here. So is that clear? Actually, I can also mention a very much relevant problem that's exact opposite of this one. So that's when I, instead of like having minimum, let's have a maximum of that. So if I have maximum x ax such that x equal to 1, so what should be the solution then? Yeah, I guess this is awfully quiet. Um, and you can put it on the chat. I know. Like, so if you know, yeah, I just want to have an idea if you guys are following. So are you thinking? Are you guys thinking? Or like, yeah, is that okay? Okay, yeah, that's what I need want to know at least the uh. So it's not clear. It's like the problem here or like why the solution earlier is like V1. I mean for this one, like for the problem earlier, for the problem earlier, what we get is the solution. So maybe I repeat a little bit. So you see, like when I try to solve this, that's like more or less the whole thing. Like it's just 2 step or 3 steps here. The first thing is like I introduce the Lagrange multiplier, absorb the constraint here. So the optimization problem we formulate into this one here. Now then when I try to solve that, what I observe is that like if I just set the gradient now is an unconstrained optimization problem, I can set just set the gradient equal to 0, right? So when I set the gradient equal to 0, then what I observe is I simply have this. A transpose AX is equal to lambda X. But what does that mean? It just means that like my X here, the solution here, should simply be an eigenvector of like A transpose A, right? Because this is the definition of eigenvector, right? You have a matrix multiplied by some vector is equal to the scale value of that vector. So this implies that like the x, the solution, or x star, like the optimum solution, the optimum will be just an eigenvector, right, of A transpose A. Now let's say like these are the eigenvectors of A transpose A. These are eigenvectors and the corresponding eigenvalues. Eigenvectors, and this is the eigenvalues here. And I have like, this is like lambda 1 less than equal, maybe this white a little bit better. This lambda n here. So the eigenvector of is like V1 with eigenvalue lambda 1 and so on and so forth. I just sorted this eigenvalue in the ascending orders. So now then x, the optimum x should be like one of the eigenvectors, right? The question will be like which eigenvectors. Now we go back to the original question here. We want to minimize ax, right? So then we just write it ax out. So that we try to write for any of the eigenvectors like vi here. Let's try to find out what is avi, the norm of that. The norm of that is just a vi transpose, or like wait one more step. This is just a vi norm of something is just avi transpose multiplied by avi. So then therefore this is equal to vi transpose a vi. Okay, by the way, your homework have something like okay, it's just like using this, but so therefore you better understand, like you will see this in homework as well, in the first homework. So then this one, okay, A what I say mentioned okay, I missed something actually. Let's see. Uh oh, actually that's all right. That's all right. This is all right. But here I actually like I write incorrectly. So let's erase this. So now VI is the eigenvectors A transpose A, right? So I will have like this. Oh, was this multiplied VI should be just like lambda I VI, right? VI here. VI transpose like this. And lambda I is just a scalar. I can move to the front. Then I have lambda I VI transpose VI. And this is just the norm, right? This is actually just equal to lambda I VI and norm square actually. So, yeah, or something like that. So anyway, so that is just equal to 1. So therefore it's just equal to lambda I. So I plug in any of this VI, like I try to X, as I said, like X has to be one of the eigenvectors, right? So then let's try like each of these. If I try an arbitrary VI, I compute AVI, the norm of that, I will simply get the eigenvalue of that. So if I want to minimize these guys, I want to minimize AX, so therefore we want to minimize AX, I should pick the VI have the minimum eigenvalue, right? So therefore I should simply pick V1 here because lambda 1 is the smallest eigenvalue. So therefore like the solution, therefore like X star is simply equal to V1. Oh, sorry, V1. So then I guess in this case, it shouldn't be very difficult for this one, right? So if I change the problem a little bit, instead of like minimizing x, sorry, minimizing ax with respect to x, let's say if I want to maximize that, I might keep the same constraint here. What will be the solution? So all the steps will be more or less the same, right? So I still can use Lagrange multiplier, absorb the constraint here, and then afterward, um, we we can still like immediately this is whole thing is the same here. So we will come up with the same conclusion that x should be an eigenvectors of like A transpose A, and so therefore like it will be one of the eigenvalues, and then we compute this guy, and AVI will still be equal to lambda I. Now this time, if I want to maximize AX, so therefore I should pick the one with the largest eigenvalue, right? Largest eigenvalue of like A transpose A. So therefore, like the solution will be in this case, immediately I will have like X star will be just equal to Vn, or like um, eigenvector of A transpose A with largest eigenvalue, right? Um, so I like to mention this actually. This is the PCA essentially. Uh, so this is a thinking. Now you think of like um, typically what's going on is like if you have A here, let's say if I have A here, in the context of PCA, will be something like you have A here is a data vector, um, a collection of data points. So let's say A is like A1 up to A hand here. And so each of these will be some data points like somewhere. So and let's do not use A n here. Let's say A1 up to AK. So let's say I have K data point And then I let each of these data points, like this is a vector, so vector, and each of this is n dimension. Now, in terms of PCA, there, like I would like to find um, a projection that the data point is most meaningful. For example, if you think of like 2Ds, maybe I have just a several more some points here, and and along if I look at like this of these points here, yeah, actually it's not. Yeah, it's okay. It's okay. We're not using PCA yet. Like maybe I don't dig deep into this one here. So if we use it later on, so um, we'll come back to this rather than like just get more into this. But I guess like one thing like it's good to realize is that like this is like essentially PCA is like doing the opposite more or less. So um I hope at least this part is clear. So solving this one. So you will see this problem like right away, like I guess like in this class or maybe like uh, in the next class. So yeah. And also you will see something like this in the homework as well. So anyone have any question? Is still unclear or like is this clearer now? Uh, no response. Uh, okay. So again, if anything is you have any question, is you can always like put your question on Discord. Yeah. So but okay, great. So let's see. Now I will move on. Like okay, finally, I'm sorry. Like that's a linear algebra. Okay. Okay. Yeah, but yes, but it's good to be able to deal with the stuff the so-called theoretical stuff. Uh, I'm actually like they are not difficult at all. Like you just need to uh sort this out once. I would say like this is actually in the long run it's like more worthwhile like to understand this kind of stuff rather than packages and so on because like packages every 5 years they just look completely different. I like to tell the stories like I learned Perl 2 decades ago, and no one know what is Perl like nowadays. So, but like this stuff that I study like in um I would say like undergrad, and they are still relevant, very much relevant. So and also like once you understand this, they don't change, and it's quite easy. What I mean easy is in the sense that it's not like every year they have a new version, like they just totally different. Sometimes even the language is totally different. So but anyway, you will see an application of this question like right away as I mentioned. And uh, but before that, hopefully it's not COVID. Before that, oh yeah, semi-positive definite. Maybe just a quick reminder, like uh, when semi-positive positive definite is something like it's used to describe a square matrix. So let's say if I have a square matrix, this is square. So n by n, let's say. So oh, actually, also it's supposed to symmetric as well. Square symmetric matrix. So therefore, I have A transpose equal to A. So when we say something is positive definite or semi-positive, positive semi-definite. I'm sorry, like I always got confused at how they order these words here. Positive semi-definite is like I have like if I look at like x transpose times a times x, this should be a scalar value, right? This is a row vector multiplied by a multiplied by a column vector here. So it should get a scalar value. if this is always bigger than equal to 0, then it's this will be like positive semi-definite. So if it's like bigger than 0, then will be positive definite. So M, maybe I don't use A here, maybe I use S here. So, and you can easily verify that A transpose A is a positive semi-definite, because like you look at A transpose A multiplied by some X and X transpose here. Of course, this guy is symmetric in the first place. This is like something like sometimes we'll miss as a beginner, that like whenever like people say like positive semi-definite, there's a assumption here, there's a constraint here that matrix has to be symmetric already, even though they didn't mention it, but it's supposed to be symmetric. And also like it has to satisfy this way. And but if I look at this one here, it's just ax transpose times ax. So this is a row vector, like this is same row vector, same it's a common vector of the with the same elements. So this will be just ax, the I elements square sum together, right? I1 to n, let's say. So of course this will be bigger than equal to 0. So its significance is like you will came across like very often, at least quite often. For example, like when you uh, play with the data, like if I I mean like data usually you model using probability, right? Um, and let's say I have some data points here. Is it's like just a vector, like as a data point, like one data point is a random vector. So the first thing, or like you want to do like typically if you have like random data points, or like this is a I shouldn't say this is a random data point, but let's say this is a random vector x here, and I can sample like in the sense that each time I can sample like different vectors x1, x2, x3, and so on. So to describe this random vector, um, the minimum information we want to have to describe this random vector will be the mean and the covariance matrix. Mean will be simply the what's the expected value for each of the element. And typically we'll make a zero mean, because I will make a zero mean will be simply I have like, let's say start with x, I say that x tilde is equal to x minus the mean of that. So so okay, for you guys, I don't know what this notation mean. This is the expectation. So that essentially, if you have taken some probability, that will be just equal to px x, something like that. So here I assume like, let's say x is a discrete. Let's make it like x is continuous. So I have like integral inside, like something like that is an expectation. So then like the covariance matrix would be something like x expectation x transpose. And the covariance say like you will more or less, if you want to process these points, you always like play with the mean, but the mean is kind of trivial because you can always like subtract the mean at the beginning to deal with like x tilde here. It will be like zero mean. So if like zero mean, the covariance matrix is simply like this. And the covariance and the therefore like the really meaningful information regarding your data points will be simply the covariance matrix, and the covariance matrix is always positive definite, positive semi-definite. So this is one example, like why, and you will basically therefore like for any high dimensional data points you're trying to process it, the minimum useful information that you will deal with that using the coherence matrix is always positive semi-definite. So therefore, you have a yeah, you have like whenever so I guess you will see that there's a significance like for that, or like in the sense like um yeah, okay, maybe I won't elaborate more on this. So let me know if you have any other questions though. So now, okay, I guess I will move on. Um, and so we are kind of like, let's see, x1, x2, x3. Oh yeah, sorry, like, I'm writing it too quickly. So here, uh, yes, x is like a random factor. Yeah. So so this random. So therefore, like this is like just x1, x2. I'm actually it's meaningless. I am writing this here. I just want to like I sample that like multiple times. So I sample this vector each time. I get something different. So I get x1, then x2, and then x3. Yeah. Okay. And I can sample more and get many of these data points here. Or yeah, the yeah the mean is here. The mean is here. Or like the mean is the mean. I should say the mean is here. But oftentimes we like to subtract the mean because once we subtract the mean, we can forget about the mean. We compute the mean, we store the mean, and then we subtract the mean. The process this the zero mean uh, uh, replacement is that the zero mean like yeah, and then like afterward. After you subtract the mean, the coherence matrix will be simply like this. So if I don't subtract the mean, the coherence matrix will be like this: x x x uh, x minus e x. Yeah, it's quite a bit more ugly. So therefore, like typically, we like to subtract the mean. Of course, this will also be like positive semi-definite as well. Uh, yeah, actually, I don't even need to mention the subtract the mean. The coherence matrix will always be positive semi-definite. Ideally, if you want to get all the statistics of this x here, vectors here, we want to have the either the PMF. Oops. Maybe just a few more words. We want to have the PMF, probability mass function, or the PDF, depending on it's continuous or discrete, right? The density function of that probability vector here. But that lists lots of information. This actually contains all the information, contain all the statistics there. Typically, we don't have this information. Instead, like the information we have, maybe it's the coherence matrix. Actually, even the coherence matrix have lots of information there. Sometimes we didn't even have the coherence matrix, but when we do, like we are way ahead ourselves. And as I mentioned, the coherence matrix will always be like positive semi-definite. So therefore, people would like to study like matrices that they are positive semi-definite. Okay, so um, now okay, I guess we will see like some application use of linear algebra now, or but first thing like it's more relevant to computation now. I want to talk about this homogeneous coordinate, or like or maybe really uh, uh, coordinate transformation. You can think of like this is like a subtitle or like uh, not subtitle like alternative title. It's like I'm looking up like coordinate transformation. For example, like just simply translation and rotation. So let's start with 2D first. Like you think of like you have an image, right? An image like or something like now 2D. So you have like some value like so you have an image is like made up of pixels here, right? So This is like the x and y coordinate. Maybe like you have 100 by 100 pixels here, right? If I look at the intensity in particle pixel here, let's say this one here, um, and now if I have a tilt of the camera, or like just make it simple, like you think of like simply the anti-image shifted somehow, maybe to the left or to the right, or like diagonalized, like by something like that. And you want to know how the image change or how to represent this change of image. So then you have this coordinate transformation here. You have the original coordinate, maybe like it's x1, x2 here, right? For one of the point here, maybe this pixel intensity, this is like I, x1, x2. Now, after this translation here, the image will move to maybe like the whole scene here, maybe like something here. The same pixel now go to here. Now, of course, like this one, the intensity is the same, but it's not x1, x2 anymore. This is like, let's say I x1 tilde, x2 tilde, x2 tilde here. Now, how do we do this transformation? Let's say this shift here is like maybe S1 and S2 shifted by S1 by S1 and S2. Um, so this is translation, right? Translation. So we just consider translation and rotation here to motivate why we want to look at this so-called homogeneous coordinate. So here I'm using this Cartesian coordinate that that is, yeah, I guess is familiar to anyone. So just a pair of numbers of the x along the x-axis and the value in the y-axis. Now, what should be like x1 tilde and x2 tilde? It should be simply, I hope it's super obvious, equal to x1 plus s1 and x2 tilde is equal to x2 plus s2, right? So if I have a translation, therefore, like the image, so new image, let's say maybe the new image is called I tilde, I tilde x1, x2, um, is just equal to, etc. Or like, let me write this way, I tilde x1, x2 tilde is just equal to I x1 plus s1, x2 plus s2, right? Something like that. Okay. Uh, any question for this one? Like anything? Uh, yeah, I guess it may be, yeah. Anything that is unclear here? Oh, okay. S1 and S2 is the shift. Maybe if I draw a bit better, that it will be more obvious. Yeah. Yeah. Okay. Yeah. Okay. Yes. So it's like something like maybe I draw a shadow here that probably like will work. Let's see. Change the color here. Yeah. Yeah. The original is here. So this point shift to here. So this is S1, S2 here. I guess it's very difficult to see. Let me, yeah. Mm, it's two. Yeah. Okay, great. So translation is like this. It's very simple. So now let's look at rotation. Oh, okay, yeah, different color again. So it's okay. Rotation. So now if I have an image again, now I rotate it somehow. I have this point here, but I rotate by some degrees here. So the point move to here. Maybe like I rotate around the origin. Um, so some from here. Oh, well, let's see. Point here. and so the original is like this. Let's maybe rotate around this point here. Sorry, my drawing is like quite a bit horrible. So so rotate by 30 degrees, but I guess it's you just this is like the origin, like this is like this is just 0, 0. So we rotate the entire image by like 30 degrees, let's say by 30 degrees here, counterclockwise. So it may be less obvious. Maybe I will just write it down. So you can um, if you don't see, maybe you see it like in geometry class. I don't know. So if you have the original coordinate, let's say it's like again x1, x2. Now the new coordinate, let's say like x1 tilde, x2 tilde. Then like x1 to with x1 tilde, x2 tilde. Maybe let me write it as a not a x1 tilde will be just equal to x1 cosine theta minus x2 sine theta. So x2 tilde is equal to x1 sine theta plus x2 cosine theta. Let's see. So say if I have like this original point like x1 and x2, right? Let's see. Just consider like a point like along the x-axis here, the original x-axis. Now, if I rotate it by 30 degrees here, now this is the new x-axis, like new x tilde, like and y tilde, like this direction. Now, okay, xy, like let's say this is like the xy, and the original xy is like that. Now if like the original point like this is like I have x1 here. Maybe I just draw a point like precisely. So if like I have a point here, okay, this one will be like x1 and x2. Now in the new coordinate here, the point will be like this, and this will be the x1 tilde here. This length here is x1 tilde here. Now how much is x1 tilde? Will be x1